video. Your favorite.
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1,000th of a centimeter in thickness. That is 10 to the power minus 3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2,000ths of a centimeter in thickness. If we fold it in half once again, the paper would become 4,000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1,024 thousandths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if you fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.
Liz, can we keep one light on? Sure. Flip it. No. No, other one. The other way. Yeah, thank you. We don't have one to work. Barely. So $100. Is this growth or is decay? Let's look. Let's look. It says it's starting with 100. It has an annual rate of 4%. So an annual rate means the bank is giving you 4% of your money every year. So that is growth. Okay. Okay. So this account is showing growth. So we're going to do y equals, and y is the amount that we're going to earn. We're starting with $100. much will we have after 12 years? So my challenge to you is, can you get this into your calculator and get the right number? Now, it's easy to go ahead and add the 1, right? So maybe in your calculator, it would be easier just to do 1.04. So we're going to try 1.04 to the 12th. Yeah, it's been a 1. It's been a 1. You got to do that too. Try it in your calculator. 1.04. So to do the exponent in your calculator, it's this button. Yeah, the y-x. 1.04. Hit the y-x. We're going to do it for 12 years.
Are we rounding?
Let's round money. Let's do this money. So that's cents, right? So we're going to have $160.10.
What?
Did anybody else get 160? Yeah.
Wow.
1.04.
I got 1.6.
Oh, then do times 100. The 100, the initial amount. The 100. Alright, so that's $60. After 12 years, are you happy about earning $60? Not really. But if it was 1,000, you know, or if you were a business owner and it was 100,000, that money is grown. They're hard money to make grow. All right, number 2. Here, this is the answer I'm looking for. On your paper, I want to see the equation. Okay.
Oh, you need to know what question we did?
Just do number 1. Label it number 1. Just practice. There's more of these in your book, so you can have a problem. Number 2, in 1985. Geez, that was a long time ago.
Not really.
That's like when your parents were born?
Good try.
There were 280 cell phone subscribers in Centerville. Which I didn't know anybody with a cell phone until I was like 10. The number of subscribers increased 75%. So there was no cell phones for a minute, and then the next year, 75% of the people I knew had cell phones. It happened very quickly. How many cell phone subscribers were in Centerville in 1994? So again, this is growth. This is kind of experiencing the way technology grows. It's remarkable. Alright, so we're going to do y equals, we started with just 285 people with cell phones, all the doctors and things. 1 plus, now 75%, we're going to convert to a decimal, 0.75. And that was 1985, so how many were there in 1984? That's 9 years later. Put it in a calculator and see, everybody selling cell phones got very wealthy right then. 1.75 y to the x, 9 times 285.
43, 80, 71, 43, 80, 70.
So for this one, guys, since we're talking about cell phone subscribers, I went ahead and rounded to the whole number. Because that's usually like human data. There's not partial subscribers. So in just 9 years, it went from 200 to 43,000. So those cell phone companies, they got very wealthy right then. You gotta find some technology right now that's growing like that. Is there any technology right now that we think is gonna get really big? I don't know. I think maybe drone delivery. What's happening? Drone delivery. Has anyone had something delivered by a drone yet? What's happening right here?
You got something delivered by drone?
I think somebody That's not creepy. It's like a drone might actually put something to somebody's house.
Man, it was 43 words.
Okay, so we can do that. Alright, let's do it again. Bacteria can multiply at an alarming rate. When a bacteria splits into two new cells, it doubles, right? So this is like the paper folding scenario. If we start with just one bacteria that doubles every hour, how many bacteria will we have by the end of one day? So will that be? Gosh, how do you do doubling? No, this is a bacteria growing. It's a bacteria. Like think of it like food poisoning is actually you get like raw chicken in your stomach. You don't notice it at first, but that raw chicken is doubling in your stomach, and then 5 hours later you're just like consumed with poison. Right? Like that's a bacteria doubling. All right, so we are starting with just one bacteria.
So, Miss, you told me you can get food poisoning from eating food that's rare, like eating rare steak.
I said chicken. You know poultry is different than rice. Okay.
I didn't.
So how do you double something? When you double something, it grows by 100%. Okay. That's how something doubles. Like you're a 100% person. If there's two of me, there's a whole other 100% person. So we're gonna convert 100% to a decimal, and we're gonna put a 1 in here. When you double, you put a 1 in that right spot. And at the end of the day, it's 24 hours. It doubles every hour. How many will be there 24 hours later? So I like to add the doubling one because it's 1 times 2 to the 24. So that's cool to see like why we associate the number 2 with the word doubling. 1 plus 100% gives you that base 2. All right, guys, what is 2 to the 24?
1 is 1.
No, we're doing 2 times 2 times 2 times 2 times 2.
So then why are you
Exponents before multiplication. Parentheses, I'm going to do 1 plus 1. Exponents and then multiplication. 1, 6, 3, 7, 2, 1, 6. Yeah, 16 million. You're throwing up at the end of the day. So you don't need a lot of bacteria, and it's the same thing with strep throat. Strep throat's a bacteria infection. You're sitting in a room, you're not really that close. Your little sister's got strep throat, whatever. You feel fine. 24 hours later, your strep throat hurts, and that's because it started with just a little bit in the air, and then it got in you, and it doubled, and the next day there were 16 million of them hurting your throat. That's how bacteria double. That's nasty, bro. So this is the data that they were putting up during COVID, and when they were showing the graphs, it was an exponential curve. So they would tell us the percent it was growing by, and we could see the curve and make predictions on it.
I can't hear you.
I'm gonna skip now to number 5. I know it's kind of blurry. I'm so sorry. Oh, it's very blurry. And then we're gonna do a decay. Go ahead and call this number 4. The population of Winnemucca, Nevada. I think that's Winnemucca. I don't know. Can be modeled, and I'm gonna write this really big for you. The population is 6,191. 1.04 to the T. So this is a very small town, 6,000. That's just like 3 high schools, and that's the whole city. T is the number of years since 1990. So this is a different type of question. They're giving you the equation. What was the population in 1990?
So what would the time be?
We're working backwards. Okay, listen. This is the population in 1990. This represents it. So what's the initial amount when I look at this equation, the way it's written? What's in the A spot?
It's 6,191.
The initial population is 6,191. What was the population in 1990? That's year one. That's what we started with. Now it says, by what percent did the population increase each year? So we're working backwards. Can you be given an equation and pull out the important data? What percent is this population increasing each year? Well, I'm tempted to say 1.04, but it's not going up 104%. How much is it going up? No. No.
Isn't it 0, 0?
It's 4. Yes, you're there. It's 4%. Okay, so if you're asked about the percent growth, you have to work backwards and take out the 1. Right? So if I was to rewrite this, it would look like this. 1 plus 0.04 to the t, right? So just be really aware. Sometimes the 1's connected and sometimes it's not. So this shows a 4% growth. You're often asked to, given this, can you pick out the initial amount and the growth? So they didn't ask us, well, what's the population in 10 years? They were just asking us about the data. Go over here on the other. You put a +1 in it. Yep. All right, let's do
number 8.
Let's do number 8.
Oh, we don't have to solve it?
No, that one was just asking you, do you understand an equation based on what we told you? All right, this is the last one on this, and then I want to show you how your book looks. This is about taking medicine. Like, you ever had a really painful ear infection, and you take your medicine, and then it wears off in 4 hours, and you know when it's been 4 hours because your ear starts hurting again? Or even like a sprained ankle? Has anybody felt pain like that where you know when the pain medicine stops working? That's what this is about. An adult takes 400 milligrams of ibuprofen every hour. Every hour it decreases 29%. And the pharmacists and the chemistry people, they know this. They know exactly how much is in your body each hour. How much is left after 6 hours? So this is a decay. It says decrease.
So
it's A 1 minus R raised to T. So we're starting with 400. 1 minus 0.29 because it says there's 29% your body uses every hour. How much is left after 6 hours? Yes, but we use a minus sign instead of a plus sign. Yes. No, this is ibuprofen. Ibuprofen is 29% every hour, but like you could take a 24-hour allergy medicine, and so that goes out every hour for 24 hours, so that would be a lower percentage. All right, so 1 minus 0.29 should be 0.71. So this means, so I went ahead and did this subtraction. There's 71% left each hour is what I see here. What did you understand? 1 minus 0.29? Did I do that too quick? I'm trying to show you that this is less than 1 now. That's how I know it's decay. Because of this, if I looked at the graph, it would swoop down. So 0.71. 6 hours later, times 400 I started with. I would write all that down, but. So I need 400 milligrams to get my ear to start hurting. After 600, there's only 51 left in there. Is my ear hurting again? Yes, it is. 51's not enough. The whole sentence? I would if I were. I'd write all that. But that's good practice for you. So now we're going to head to chapter 6.4 and look at the way these problems are presented in your book. An idea of your worksheet from yesterday?
When we had it as a class.
Yeah, I finished the last three for library.
Yes.
I want you to attempt 1 through 6 and 9 through 11. Kind of a lot.
This is homework.
Yeah, you will have some to do at home. You will. All right, it says identify the initial amount A. Can anybody tell me A in number 1? Negative 3501. And the rate of growth R as a percent. Can anybody tell me R? Thank you. Oh, my bad. And then it says evaluate when t equals 5. So it gives you a chance to practice with your calculator some more. Round to the 10. In the bold directions, it says evaluate when t equals 5. Yeah. So for all of these 1 through 6, we're doing t equals 5. So this is like 75% growth. This is like literally if you had $350 in the cell phone bill. How much it would
cell
bring?
phone bill is crazy.
Boom. All right, number 2.
Where this at, y'all? Oh, this in the book. They tripping.
I feel like you don't need my help.
It's SATs, yeah.
I'll do anything I can do.
It's already added.
Yeah.
Yeah, so you have to kind of take apart that one yourself. Number 3. You might want to consider like thinking 1 plus 0.2. Yeah.
Miss, so all these are the time is 5, correct?
Yep. So A is 25 and R is actually 20%. Not 120%. Because that's except for the 1 and the 0.2. So you got to think back. Oh, there was a 1 plus here. So you have to take apart.
Ooh, we just controlled you. Yeah.
It's not difficult, but you just have to